Hello everyone. So we are on day 19. I might sound a little low because I have a little fever. But yeah, if we go to the day 19, we see that today we have to implement what we have learned the theory yesterday, attention mechanism. So we know what it is. I have posted, not I have not linked it here, but you can get the all the posts up to day 11 from this um, site called akash.com, my tech journal. uh, so yes, here we can see we yesterday we have explored what attention this attention mechanism is, how it assigns scores calculated by normalizes it, and then on the basis of that, how it calculates that which how it calculates the importance of each word in the numerical form, which will be used to generate the output. So this is the whole crux of the attention mechanism. Uh, let's go and use the same ChatGPT context window to start. So I'll say, I'll minimize, hide it. I'll say, hey, today is day 19, and today we will continue and test it. So let's wait for ChatGPT for it replies. Let me go and put it in on the top. Um, let's wait for it to generate the response completely. Okay, it is almost done. So we can go back to the first step. So yes, if we start, uh, so let's say it says that today we will implement the attention mechanism with LSTM to perform a machine translation. This implementation will make our LSTM model more powerful by enabling it to focus on specific parts of the input sequence when generating each word. Exactly. In this project, we will build an encoder decoder LSTM model with an attention mechanism that helps improve translation quickly. Let's get so it is going to be an encoder decoder an LSTM mechanism, a model, and the aim is to translate with quality. So we let's import the necessary libraries. So let's go to the PyCharm, create a new Python file, and yes, add it to our Git repository. Mention what the problem is. Problem is understand, implement attention mechanism. So let's come here. Attention mechanism for learning machine learning. So import. Let's go here. Import what libraries? We have to import NumPy, TensorFlow, layers. We have to get input LSTM, DINs, and embedding and dot layer. Then model, and then from keras reprocessing sequence, pad sequence. You have used this pad sequences on day 17, so we know what it does. It fills the empty uh, spaces, or it trims the large words, whatever you pass. So let's import numpy as np, import TensorFlow as TF, import from TensorFlow keras dot layers, import input layer dot layer, LSTM layer, dense layer, one more layer, right? Embedding activation. So input LSTM dense embedding dot and concatenation. Done. From TensorFlow dot keras dot models, import model from TensorFlow keras dot pre-processing dot sequence import pad sequences. That is all. Let's come back to we see couple of new layers: input layer, dot layer, and activation layer we are going to use for the first time. uh, it says that we will need this layers for the active attention mechanism. So let's do data preprocessing. Data preprocessing, we will use sample data to demonstrate the working of the attention based LSTM for machine learning. Translation: for example, for this example, assume that we have the following prepared data set: sequence of words in the source language, sequence of words in the target language. Input tokenizer and target tokenizer are they are used to convert the words into numerical indices. So we are so sequences of words in the English. Let's say we have to translate it into French. So target sequences will contain the sequences of words in the uh, 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 in the let's say French language. So assume we have preprocessed data ready. So okay, so let's go with the flow. Pre data. So we'll say max encoder sequence length, max decoder sequence length, vocabulary size input output 10,000 10,000, and embedding size is 128 dimension vector. Max encoder size sequence length, what length? 20. Max decoder sequence length 20. Max input vocab size 10,000. Not max input vocab size, output vocab size 10,000, and dimension 28. And I have a typo. Guys, now we are going to do input sequences. We are going to use random wa- ran int uh, vocabulary input vocabulary size, and then 1000 into uh, max encoder sequence length. Let's do what? I have a typo again here. Output sequences. This will be output vocab size, max decode. Why are we doing this? Though I did not understand, so let's understand. So max encoder decoder sequence length. Set the maximum length of input and output sequences for training. Okay, these are the vocabulary size for the target language. So let's print this. Print input sequences. Print output sequences. Let's run this file. Day 19, and we have a typo here also. Python. Oh yeah. Um, So it generates the output of thousands. So if I say this length shape, 1000 into 20 is the shape. So it has 1000 rows, and each row has 20, 20, 20 columns. Uh, what is this? And the number is generated between 0 to 10,000, 0 to 10,000. See, so the length, so the range for the numbers is 0 to 10,000. So the numbers are generated between 0 to 10,000. And how many numbers are generated between 1000 to the 1000 into 20, so 1000 rows and 20 columns, 20 columns. So 20 columns, yes. So now build the encoder. Define. We will start by building the encoder part of the model. The encoder processes the input sequence and generates hidden state for each time step. We are we are then used in the which are then used in the attention mechanism. So it says we will start by building an encoder part of the model. The encoder processes the input sequence and generates hidden shades for it. Okay, so we'll start with the encoder part of the model. It processes input sequence and generates hidden. Okay, so the work of encoder is to generate the hidden states by processing the input sequences. So it uses the input layer. We pass the input sequence length, and then we have another embedding there where we pass the dimension, input dimensions and the output dimension. And then we have the LSTM layer, has 128 neurons with the sequence of 128. We say, okay, do we want to make the return the hidden states? Yes, we want to return these hidden states, so that is why we have this return sequences true and return state true. Then we have encoder output. We encode the this input sequence and save the data into state H and state C. So let's do that. Let's write it. And similarly, we will do for the decoder. The decoder generates the output sequence, and here we add the attention mechanism to help the decoder focus on relevant parts of the encoder part output at each step. So we define the decoder also in the same way. Correct. Uh, Here we pass the initial states, hidden states from the encoder to the decoder. And then add attention mechanism, which we have learned yesterday, is to dot product the encoder and decoder. Then apply softmax to convert it, not to normalize, and then calculate the context. If we see with the help of example, to calculate the to create the context vector by by having the dot product, and then some adding up everything. So we come back here. Yeah. Uh, and then we concatenate. This is what we are concatenating here. When we need to do concatenation and context and decoder output, and then we decode, add a dense layer, and the final decoder. Okay. Okay. So that is done. then we create the model, train it and test it. So let's start. The code looks pretty easy. This is all what we have learned yesterday. So first we'll define build an encoder. Build an encoder. So let me minimize this terminal. Give ample space lines so that the code remains in the center. So first is build an encoder. So we'll say encoder inputs input layer, which will have the shape of maximum encoder sequence length. Then we have another layer, encoder embedding layer, and embedding layer will have what the input dimensions are going to be. uh, Input vocabulary size, and the output dimensions are embedding how many embedding dimension, how many size vector you want, 128 size vector you want. And the input for this layer is going to be the previous layer. And we have a typo here as well, so it is going to be embedding. Then we have encoder LSTM, and we have LSTM layer of 128 neurons. Do you want to return the hidden states? So yes, return sequence is true, return state true, and then we return it. Encoder outputs state hidden state sequence typo. Encoder LSTM. Here we pass the encoder embedding that we have created. Here in this layer we pass the encoder embedding. Okay, once done, now build the decoder. Define input shape max decoder, and then we have decoder embedding. So here embedding, the input dimensions are max input vocab size, not input, output vocab size. Output dimensions are embedding dimension 128 vector. Here the input for this layer is decoder input, and then decoder LSTM layer of how many neurons, 128 neurons. Return sequences true, return state true. Then we have decoder outputs will have what, uh, decoder LSTM decoder embedding, and the initial state will be the state H and the state C that we have got from the input building, and that we have got from while building the encoder. Now we have the attention mechanism. MECHANISM. Build. We have to build what? Attention. What we have to do if we go from this last to yesterday's understanding, we have to do scoring, weighting, and context vector steps. So scoring will be done like how our scoring will be done like dot product of how many axes? 2. So we are doing a dot product of in each of encoder and decoder output to get the similar score. So we have dot product of uh, de- decoder outputs and encoder outputs. Now we calculate the score weight. We normalize it by applying softmax activation. So attention again save it to the same variable. So activation of softmax from this layer, the input on attention, and then we again do a dot product of attention that we have got like this and this. So a two-dimension attention that we have got and the encoder outputs. So softmax. So it is context. So we do dot product of attention and the decoder outputs. Let's do what? Let's look at the decoder output for once. Print decoder outputs, print encoder outputs, and run it. It is a tensor, Keras tensor of shape 20 into 188, 128. So it has 20 vectors of size 128. Okay. Okay. So it is a two-dimension thing. So da, 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 da. Actually, I'm making a mistake. So we have to do on encoder outputs. Yes. Now we concatenate the vector with the decoder LSTM output. Decoder output, decoder combined context, combined concatenate access 1. What are we concatenating? Context that we have created is this, and then with decoder output. Okay. Context and the decoder outputs. Once done, we do what? Finally, the concatenated output passes through the dense layer with softmax activation to predict the next word in the sequence. So it applies softmax activation to predict the next word in the sequence. So now we'll have decoder a dense layer. We create dense how many neurons we want. Vocabulary output vocab size. Activation is softmax. Why we need softmax? We have understood it yesterday. So decoder output output decoder dense layer. In this dense layer, what are we passing? Decoder combined text. Correct. This above context that we have created, and I have a typo. So that is it. We have built the. Let's print the decoder output final once. Let's remove this line and run the script, and the output is like this again. The 10,000 vocabulary size, the sequence vocabulary size, and the 20 factor 20 rows. Now we create the model. So define the final model. So the model is model. Here we pass encoder input, decoder input that we have created, and then final decoder outputs. So encoder input, decoder outputs that. So we have to convert from this to this, translate from this to this, and then apply it on the decoder finally output, and then compile the model with optimizer Adam, and then since we have is this a category type? Yes, it is category type. So categorical cross entropy and matrix accuracy. So loss categorical cross entropy. This will throw an error, I guess. We'll have to change it to sparse or class. Matrix will be accuracy. Why do I know this? Because we have encountered something similar in our previous problem. So let's print this summary. Let's run the model one time. Clear the terminal. So no error. Then we are going to do what? Train the model. So it is train the model. So it will be model dot fit. We pass the input sequences. The target sequences is put the decoder input. Targets are offset by 1. As the model learns to predict the next word based on the okay. So we are doing an offset 1 because, and then we are excluding the last token. Okay, because it uses the previous word to predict the next word. So that is why we are doing. So it is going to be input sequences. Sorry, it will be in a vector, and then target. Did we build? So this is the output sequences. So instead of target, we are going ahead with output sequences. So this is the output sequences, and output sequences we are doing what? Offsetting with I mean offsetting with -1, because we are using the previous letter word to predict the next word. And then we have output sequences, output sequences uh, offset by 1, so to predict the next, and we are leaving the last, because yeah, these are the input and we are predicting the next word. The for example, I have I m, so I is the input. I will come here and m will be left here. Here it will start with m, it will leave the I. So now we'll have batch size 64, how many epochs we are taking, 10, validation split 0.2, use 20% of the data for validation or as unseen data. And then we have test the model. So let's test the model. Testing the model. How do we test it? Once trained, we can test the model by generating translation for new input sequence sentences. We will use the encoder to encode the input and then use the decoder one word at a time with the attention mechanism to produce the output sequence. Okay, so it takes the input sequence. So it encodes using encoder LSTM that we have created. If you remember, we have created this encoder LSTM layer earlier. So we will encode it, get the encoder output state in H, then initialize the decoder, input with the start token, and then we use the previous layers to generate the next words. I'll say where are we calling this function. We are defining this function, but where are we calling this function? Okay, it is trying to add. So it is a utility function. We are not actually calling it. It is just saying that we are calling it. So we have to pass the inputs and sequence like this. Can I? So it makes the. I don't think I need to write this complex thing because it does not make sense for now. But I say What if I want it to legit convert an English sentence into French? How would I do that? Don't edit the previous LSTM MD talk. Give me with as like a normal non MD response. So if I legit want to convert, let's say I am learning deep learning to Je suis en train d'apprendre this profound. I don't know. My sister speaks very good French. She would have hit me very hard. So if we would have to convert it, we would have to create the input sequences and output sequences from this, and then yeah. And then we can use that translate sequence function that we have created earlier to translate it. Hmm. So what we would have to do, we would have to import another package called tokenizer. uh, so let's do that. um, I'm importing from TensorFlow keras preprocessing text import tokenizer. Okay, done. And then we example tokenizer. Here I'll have import. I'll minimize it and then update the existing code. Tokenizer is a tokenizer of a number of words, 1,000 words. Vocabulary size. Input vocabulary size. Output output tokenizer number of words, output vocabulary size. Then we have input sequences, input sequences. I see. I'll just copy it. These are the input sequences, and then we have output sequences. Instead of target sequences, I'm just saying it output sequences. So it has the conversion for each input, each sequence, and this is it. And then we fit on text. Input sequences will be, so input tokenizer tokenize the input sequence, fit on text this input sequence, output tokenizer fit on text output sequences. And then we have to convert it into sequence. Input sequences will be converted to input tokenizer text to sequences. This input sequences, and same with output sequences. Output tokenizer text to sequences, output sequences, correct? And then we apply padding. Input sequences will become apply padding to the input sequences. Max length 20 and padding will be applied. Post output sequences will be out apply the padding on the output sequences. Padding post, and then we just comment it. We are not going to use random function to generate it. Once done, let me close it. We are done with it. We are done with it. We are just now going to once your model, so the model training is going to be same. So we'll say once the model is trained, we can use translate sequence function to translate new English sentences to French. How to adapt the function to translate an English sentence will be process the sentence. First tokenize and pad the English sentence. So first we get the sentence, we use the tokenizer to tokenize it, and then apply padding. Once done, then we use the translate sequence function to translate it and output it. So I'm going to use the function as it is, and then we are going to understand the function later. So I'm going to copy this thing and create a function out of testing model. So we are calling those layers to translate and then output break when we reach the end. Now once done, let's test it first and then see if it is worth understanding or not. So yes, um, test for a new English sentence. So I'll say sentences. Hey, how are you? I'll say hey, how are you? So first we tokenize it. We use input tokenizer to fit to text. Use converted to fit to so converted into text to sequence. Pass this sentence, or I can use this also because I'm passing limited input sentences to train it, right? So I'll use this line only. So I have tokenized the input sentence, this testing sentence, converted into sequences, and then we are going to apply the padded sentence will be pad sequence apply on the input. uh, so update the sequence. So this is, let's update test sentence test sequence. It is going to be pass the test sequence input to here we the max length is going to be max length. What is the max length that we had started with? Max encoder sequence length maybe, and the padding will be applied post. Done. And then we simply translated using translated sequence using the translate function. Translate translate sequence function and pass this input sequence. So it is simply going to be input test input sequence. So that's it. Just pass that and print as a translated sequence is translated sequence. Let's run it, clear it and run it. I have a typo here. Hopefully this should. Okay, so we have a lot of typos because here we are using a different name. So a target tokenizer is different here. If I open this, target tokenizer is so target tokenizer is where did we create a target tokenizer? Have we imported it anywhere? Uh, so we are importing it, but we have not created it. So let's do what? Let's import this target tokenizer output tokenizer. Yes, use instead of this, let's use this output tokenizer. This should work. So we had an error in the original function. That is why I was reluctant to use it first. We have the error again at line number 70. So let's go to line number 70. Um, hmm, so we mention it. Okay, so I have a typo which I did not use this comma. So that is what I was passing currently. It is a two-dimensional vector. So let's run it again. And I have error at line number 19 again. So it says now this. I do understand why we are getting because we are doing this. Hmm. We have lots of error from today. Hmm. So I did made some adjustment to the code and to make it work. So what adjustments I did is if we look at the code here, we got the input and output sequence after adding padding. After that, we retrieve the start token from the tokenizer, and then we build the encoder first. Once we are done with the encoder, everything, all the steps are going to be same. We build the decoder the same way, and then we I add the attention mechanism of scoring and then normalization using softening and then creating context vector, and then we train the vector on the decoded inputs from here only after that here. uh, and then we built the decoder and then we added the decoder to our model. We did that later, so earlier we were doing it first. So now if I ran the script, I still was not able to generate the translated sequence. And one of the reason was that the input for this model is too less. Here we see we have only two input sequences for generating for training the model, so that is too less. So that is why maybe it is not generating it nicely. So if we look at the code, so this is one of the reason the model has predicted that this could be one of the reason. Two sentences too is far too small. Ideally we would be needing thousands of pair of sentences for the model to understand sentence structure translation. But since it is the epoch training is doing well here, we can see the accuracy loss and everything. Like the accuracy is 55% and the for the validation accuracy 60%. So I can park it for now, that okay, it is working fine. Since the testing is not working at all, so I'm not, what I'm going to do, I'm not going to have this thing at all. So I will simply go and remove it. And remove it, if I remove it, because this is not working, so what is the need of understanding a code which is not working while we are starting to learn something new? So I'll park that thing for now and just leave it at this step, where the accuracy is 55% and for validation data the accuracy is 60%. And this thing we have already understood. So let's do what, let's conclude the problem for today. So I'll say commit it 19, commit uh, explore. So the commit message will be day 19. Understand attention mechanism on LSTM. Okay, and then add it, push it to the main branch. Let's go here and we should be able to see the code. Yes, the code is here. So yes, we can conclude it and then we can come back tomorrow for problem number 20 to understand the autocoder, build an autocode encoder based on anomaly detection system. So thank you very much.